In the previous video, I spoke about the first two steps of training, forward propagation and using a loss function to evaluate how good or how bad the forward propagation guess was. In this video, I'm going to talk about back propagation, and then we'll implement a neural network that has a loop that performs all three steps of training. This neural network will learn how to solve the XOR problem that I mentioned in the previous video, and it'll be implemented using just Python and Numpy. No deep learning libraries will be used. Backpropagation involves changing the weights of the neural network so that the network makes better forward propagation predictions. Implementing backpropagation by hand without using a library like Keras or Tensorflow is tricky because it involves figuring out the derivatives of the loss function in terms of the weights and biases of the neural network. To implement backprop, let's build what's called a computation graph. A computation graph is just a visualization of all the computations that happen during forward propagation. I'll go back to those forward propagation equations we saw in the previous video. So here they are right here, these three. The computation graph is just a representation of these three equations. So let's look at the first equation. See how a weighted sum is performed here inside the brackets, and then the sigmoid function is applied to the weighted sum? Well, the computation graph just breaks up this equation into its two parts. Z1 is set equal to the weighted sum that was in the brackets, and H1 applies the sigmoid function to that weighted sum. And the same thing happens with equation number 2 and equation number 3, which was computing the output of the network, at that A node. Similarly, that's broken up into two parts. So we're not seeing anything new here. The computation graph has just broken up that first equation into two parts here, and it's done the same thing with the other two forward prop equations. Forward propagation goes from the input layer, for example, let's say x1 equals 0 and x2 equals 1. So x1 is input into this stream and x2 is input into this stream. The h1 and h2 values are computed in the middle part of the network, and then a, which is the final output of the neural network, is output. The error of the neural network is then computed by this loss function. The output value of the network A is compared to the target value Y. Then backpropagation happens. Backprop moves in the opposite direction of forward prop, as you might guess. It moves backwards from the loss function and back to the middle layer and then back to the input layer. As backward prop moves backwards through the network, it's adjusting the weights of the network. It adjusts W5 and W6 and B3 first, and then it adjusts the weights in the middle layer, so W1, W2, B1, and W3, W4, and B2. Backprop adjusts the weights so that the neural network will output a better prediction than it did on the previous iteration of forward prop. So we want to compute the derivative of the loss function L with respect to A, and that's what this DLDA term means. In other words, we want to know how the loss function changes when we make a change to the value of A. If A gets decreased a little bit, for instance, does that make the loss function increase or decrease? And that's what this term DLDA tells us. Similarly, we want to compute DA/DZ and DL/DZ. DL/DZ, for instance, means if we increase the value of Z a little bit, does that make the loss function go up or down? We want to compute these three terms because they help us compute what we really want to know. We're not actually interested in these terms, but really we need them to compute what we're really interested in. So what are we really interested in knowing? We're really interested in computing DL, DW1, DL, DW2, DL, DB1. Similarly, DL, DW3, DL, DW4, DL, DB2. And DL, DW5, DL, DW6, and DL, DB3. DL, DW1, for instance, tells us what happens to the loss or error function when we increase the value of W1, for example. Similarly, DL, DW2 tells us what happens to the loss or error function if we increase the value of the W2 weight. Knowing these derivative terms enables us to adjust the weights and biases of the neural network so that it learns to make better predictions. So for example, after doing forward prop and computing the error, we might find that increasing the weight W1 will make the neural network output a better prediction. That's what backpropagation finds out. It finds out how to modify the weights and biases so that the neural network makes better predictions. That's what my note here says. We want to compute these 9 blue terms because they tell us how to modify the weights and biases of the network so that it makes better predictions. So let's compute this DLDA term first. We use calculus to compute the derivatives of a function, and I'm not going to talk about the steps to take for computing the derivative, but I show the steps here, and you can pause the video at any point to see how the derivative is computed. And when we've gone through all the steps, we find that DLDA equals this term here. So we've computed DLDA. Let's now compute dA/dz. Here are the steps for computing dA/dz. So the derivative of dA/dz is a times 1 minus a. And now let's compute this dL/dz term. We can use the chain rule you learn about in calculus to compute dL/dz. Turns out that dL/dz, when you work it out, equals a minus y. So I'll just make some room here. Remember that we've computed these 3 derivatives because they help us compute what we really care about. We really care about the derivative of the loss function with respect to the weights W1, W2, W3, W4, W5, W6, and the 3 biases B1, B2, B3. That's what these terms in blue are. We use the chain rule to compute these derivatives. So first of all, we need to compute what dL/dH1 and dL/dH2 are to compute these first 6 blue terms. And to compute the last 3 derivatives, we need to know what dL/dz is, but we already found out that that's equal to a minus y. So here are the steps for computing dL/dH1 and dL/dH2. You can pause the video to look at the details. So now we know what the equations for these orange terms are, and we'll compute the other parts that we need to know in order to compute the first 6 blue terms. Again, I'm not going to talk about the derivation of these equations, but I show them here so you can pause the video at any step if you're interested in the details. We then compute the last 3 blue terms and we're done. We found out what the derivatives of the loss function are in terms of all the weights and biases of the neural network, and these derivatives are then used during backpropagation to adjust the weights of the network so that the neural network learns to make better predictions. Let's look at how I've implemented forward propagation and backpropagation in Python. So we just import Numpy here. The matrix X, which is defined here, those are the different values that x1 and x2 can have, as we saw in that XOR truth table earlier. So both x1 and x2 can equal 0, or just one of them can equal 1, or both of them can equal 1 here. And these are the corresponding XOR outputs. So for instance, 0 XOR 0 should output 0. 0 XOR 1 should output a 1, etc. 1 XOR 1 should output a 0. In this part of the code, I assign random values to the weights and biases of the neural network. And down here is the loop where we do the 3 steps of learning. So this loop executes 40,000 times, so we're taking 40,000 training steps. And here we're getting values for x1 and x2 from that matrix X that we saw up above. And this part of the code, we're doing forward propagation. So forward propagation outputs a value for the network. we compute the loss here. The loss function here indicates whether the neural network made a good prediction or not. Now this part of the code, this is where the 9 blue derivative terms that we saw earlier, that we spent a fair bit of time deriving, they're defined here. And the weights and the biases of the neural network are adjusted here. They're increased or decreased a little bit based on what the blue derivative terms turn out to be. It looks like we're just decreasing the weights here on each iteration of the loop because these are all subtraction signs. But a blue derivative term like dl dw1 will sometimes be positive, and at other times, so in other iterations of the training loop, it will be negative. So sometimes we're subtracting a positive number from a weight, which means we're decreasing the weight, but other times we're subtracting a negative number, which means we're adding to the weight, we're increasing it. You might be wondering what this alpha term is. It's a value, I think it's set to 0.01 in my code. It's some value smaller than 1 because we want to adjust our weights only a little bit on each iteration of the training loop. If we adjust the weights too much, we might overshoot what their proper values should be to solve the problem. I'll run this loop where training happens, and we should see the loss function decreasing as the loop executes. So the error or the loss function starts off at about 0.3, and as I scroll down, it should get smaller and smaller. Yeah, it decreases to basically 0. It's still executing because we take 40,000 steps. So I'll just wait for it to finish, the training to finish. So the loss or error is 0, which means the neural network has properly learned how to represent the XOR function. Now that the neural network has been trained to try to solve the XOR problem, let's see whether it really does solve the problem. So let's say x1 equals 0 and x2 equals 0, and let's feed those values into our trained neural network and have it do forward propagation. If the neural network is working properly, it should output a 0 because 0 XOR 0 equals 0. So I'll run this cell, and yeah, we get a value really close to 0, so that's the correct result. Let's keep going and see how it does when x1 equals 0 and x2 equals 1. It should output a value close to 1 in this case. And we get a value 0.99, so that's the correct answer. Now let's look at when x1 equals 1 and x2 equals 0. This should also output a value close to 1, and it does. And finally, when x1 equals 1 and x2 equals 1, the neural network should output a value of 0, and it does. So in these two videos, I've shown you how to implement a neural network from scratch by defining the forward propagation equations, the loss function, and the derivative terms for back propagation, which we use to adjust the weights and biases of the neural network inside the training loop. Thanks for watching.